Okay, hey everyone, this is Connor Mead with the Calculation Center again, and I'm here with a video on linear algebra, and this time we'll be dealing with eigenvalues and eigenvectors for 2x2 matrices. So let A be a square matrix. We say a vector V and a number lambda are an eigenvector and an eigenvalue of A if they satisfy this equation here, which says A applied to V is equal to lambda times V. Okay, so this just means that when we put V into A, we get out the same result as if we had just stretched out V by a factor of lambda. Okay, now I just want to make it clear that we can't really use the techniques we've developed so far to solve this problem immediately, because we're able to solve equations of the form AV bar is equal to some constant using the pivot algorithm and things like that. But we can't actually do that here because we've got two unknown variables. We've got the vector V is unknown, and this red lambda is also unknown. So we can't really just kind of try and do row reductions or anything like that. Instead, we'll go through what we have to do in the form of an example, and hopefully we'll generalize from there. So we're going to let A be equal to the matrix 2, 3, 4, 1, and the aim for us is to find all eigenvalues and all eigenvectors. Okay? So how do we do this? Well, step one for all of these things is to compute the characteristic polynomial. So we compute CA of lambda, which is defined to be equal to the determinant of A minus lambda times the identity. Okay, so this is going to be some function depending on lambda. But we work it out in general. So determinant A. So first of all, this is a determinant of a linear map. The linear map here is A minus lambda times the identity, and A minus lambda times the identity is just we take off lambda from the diagonal of A. So this is equal to the determinant of 2 minus lambda, 3, 4, and 1 minus lambda. Okay, and this is therefore equal to 2 minus lambda times 1 minus lambda minus 3 times 4, right? Because that the determinant of a 2x2 matrix is the first times the fourth minus the second times the third. Okay, let's keep this tidy. Okay, so this is the characteristic polynomial of lambda. Let's just multiply it out so we have it in a nice form. 2 minus 2 lambda minus lambda plus lambda squared minus 12. So this becomes lambda squared minus 3 lambda minus 10. Okay. The second step, 2, is to find roots of CA of lambda. And that just means, i.e., lambda values such that CA of lambda is equal to 0. So this thing on the right here depends on lambda. It takes on different values depending on what lambda is equal to, and we want to find those values such that it's equal to 0. Okay? And to do that, we're going to do, well, you probably know a lot of ways of solving quadratic equations like this. We're setting lambda squared minus 3 lambda minus 10 equals 0. We're just going to do it the reliable way, which I guess is by using the quadratic formula, which says that the roots is given by minus b, so that's 3, plus or minus the square root of 9 minus 4 times AC. AC here is minus 10, so it's plus 40 over 2. So this is equal to 3 plus or minus 7 over 2. So I guess it's equal to 5 or minus 2. Okay, so these are our two eigenvalues, is what we say now. We say that this implies 5 and minus 2 are the eigenvalues of A. Eigenvalues of A. Now, recall that we're trying to solve the, I better get a copy of A just briefly so that we can work with it. But recall that we're trying to solve the eigenvector equation. So this is our matrix. I'll just put in the brackets again. This is A here, and these are the eigenvalues, 5 and minus 2. Okay, and we're trying to solve the equation A v bar is equal to lambda times v bar. Now, you might remember earlier on I said that we couldn't solve this equation because it wasn't the kind of equations we were used to. We didn't know what this v bar was, we didn't know what this lambda was, we don't know what this v bar was. Admittedly, these are the same v bar, but we didn't know anything about it. But however, now we know lambda is either equal to 5 or lambda is equal to minus 2. So we can just set lambda equal to 5 first, and then lambda equal to minus 2, and we'll find all our eigenvectors. So first, let lambda equal 5. Then, just to be clear here, solving a v bar equals lambda v bar is the same thing as solving a v bar minus lambda v bar equal to 0, which is the same thing as a v bar minus lambda times the identity applied to v bar equal to 0. And by the linearity, we get a minus lambda times the identity applied to v bar is equal to 0. Now what this means, since we know lambda is equal to 5, this means we're just solving the equation 2 minus 5, 3, 4, 1 minus 5 applied to v bar is equal to 0. And turning this into augmented, this is in the case lambda is equal to 5, of course. Turning this into an augmented matrix equation, we get minus 3, 3, 4, minus 4 applied to v bar is equal to 0. And this, oh, well, to be clear, this should probably, if we wanted to be consistent with how we're doing this, should look a little more like this, I guess. I'm going to assume v bar is equal to v1, v2 for notation. But these lines clearly cancel with each other, because if I multiply this by minus 4 over 3, they'll become the same line. So we get minus 3, 3, 0, 0, 0, 0. And this implies v1 is equal to v2 after we divide across by 3. So therefore, v bar is equal to v1, v1. So this implies lambda equals 5, and v bar is equal to, let's change v1 to x. X is an eigenvalue, and vector pair, an eigenvector. I should write if I want it to be complete, but it's just to save a bit of time. It's eigenvector pair for all x. Okay, so no matter what value we choose, of x we choose, lambda equals 5 will always be an eigenvector or an eigenvalue for the eigenvector xx. Okay. Now remember, we had another choice of lambda as well. We had lambda equals minus 2. So let's just go over here, I guess, and solve that quickly. Lambda is equal to minus 2, and just jumping straight to the kind of problem we're trying to solve, we have to subtract off minus 2 from the diagonal. So this becomes 4, 3, 4, 3. Because remember, subtracting off minus 2 is adding 2. And this just becomes 4v1 plus 3v2 is equal to 0. So v1 will be given by minus 3 over 4 v2. So therefore v would be equal to minus 3 over 4 1 times v2. So therefore vectors of the form, this implies minus 2 and minus 3 over 4x. X is, again, an eigenvalue, an eigenvector pair for all values of x. Let's copy that text over here because it's the exact same thing. But this is the idea of how we find eigenvectors and eigenvalues for 2x2 matrices. Okay, so we'll go on to some more difficult eigenvalue problems in the next video, but hopefully this all made sense to people. And until next time, I'll see you then.